Hi everyone, my name is Yuntao Du. It is an honor to share our work, LDP trees, locally differential privacy trajectory synthesis. This work is a joint work that with different researchers from Zhejiang University, Purdue, Stanford, and Singapore Management University. So I will first introduce the motivation of this work and then provide some basic knowledge and related work. Then I will present our method and show experience results. And finally, I will conclude our contributions. So the recent years, we have seen many horror news from data release. For example, attackers could use GPS data to track someone's house, working places, or even secret military bases. And even with some privacy-preserving techniques like anonymization, those personal information can be easily revealed, which is a serious problem for anyone who wants to release data set to public. So despite all the issues that may incur when publishing data, more and more data sets are available on internet because they want to make the best of users' data. This is especially true for trajectory data. Government can use trajectory data to monitor and improve traffic condition. Doctors can use trajectories to analyze and forecast diseases spread, like COVID-19. And there are many apps that use people's location data to provide timely services. So therefore, the question is that how to release trajectory data without sacrificing users' privacy. So differential privacy has become a golden standard for protecting sensitive data while ensuring individual privacy, which has been adopted by many government and companies. And the goal of differential privacy is to learn nothing about an individual, while learn useful information about a publication, which can be achieved with some random algorithms like a perturbation. Centralized differential privacy has been extensively studied for several years, which assumes that there is a trusted data aggregator which has all the original data. So, however, for many situations, the data aggregator also cannot be trusted. So, recent years, local differential privacy has been studied. Local differential privacy assumes that the aggregator is also untrusted, which is a very strict privacy algorithm since that no one except the data creator has access to the raw data. So LDP is good, but hard to achieve a good balance between privacy and data utility. A trajectory publication under centralized differential privacy has been extensively studied for several years. Generally speaking, there are two kinds of methods to public privacy preserving trajectory data. And the first is the perturbing-based methods, which means that we add noise to each location and use those perturbed points to construct new trajectories or answer spatial-based queries. The second one is generative-based methods, which collects important features and add noise to them, then use them perturbed features to generate sensitive trajectories. However, in local settings, since we can only access user local trajectories, it is much harder to preserve data utility for publication. There are so few works that they can meet the strict privacy requirements of LDP, and those works suffer from poor utility, additional public knowledge dependency, and high computational overhead. So first, the task of this work is to build a generative model by extracting key movements from individual road trajectories and output the synthesized trajectories. And the synthesized data should satisfy all four properties. First, the whole synthesized process should strictly guarantee local differential privacy to preserve users' privacy. And the second is that the synthesized trajectory should resemble true trajectories from different aspects, such as spatial and statistical aspects. And the third is that it is equally important that the computational overhead should be small because the computational resources of many GPS-enhanced devices, such as wearable devices, are rather limited. Last, it would be better that the synthesized data can against the common location-based attacks. So there is a framework of our method, LTP trace. Instead of directly perturbing location data, we aim to extract the key movement patterns of each user and use them to synthesize realistic trajectories. There are three main components of LTP trace. The first is the length distribution, which can indicate the travel distance of users' motions. And the second is mobility model, which estimates the transaction patterns of trajectories. And the last is the beginning and terminate transactions, which could indicate the start and end points of trajectories. So for trajectory length estimation, we perturb the trajectory length locally and report them with optimized unary encoding, which is a popular LDP protocol for frequency oracle. And after all the perturbed lengths had been collected by the data curator, we aggregate them to estimate the distribution according to its proportions. So for mobility estimation, we model the transactions of each trajectory with one order Markov chain and report them to data curator with optimized unary encoding. And the question is that how to select proper report times. If each trajectory reported transaction information too many times, the privacy budget for each transaction would be small, which would lead to large noise. And on the other hand, if the report times are too few, the estimation bias would be dominant. So there is a trade-off between the small estimation bias and the small perturbation noise. So we tackle these problems by using the case quantile of estimated length distribution. So that the optimal case should balance the noise error as well as the estimation errors. And the final component that we would like to model is the beginning and terminate transactions. We separate this from other intro transactions because they can only occur once for each trajectory, and on many situations, they can play an important role to identify users' information like pickup locations, home and workplaces, and etc. So what we do is add in special virtual start and end points for each trajectory and use them to report the beginning and terminate transactions to form the final trajectory mobility. So, and this is the overall synthesis algorithm for LDP trace. So as it shows, during synthesis, we first randomly select a target length from length distribution and sample a start point for virtual start transaction. Then iteratively sample the next point according to the learned Markov chain until it reaches the target length or virtual endpoint. And for experiments, we use one synthesized dataset and three real-world datasets to evaluate performance. First, we evaluate utility in three aspects: a global level, trajectory level, and thematic level. So our method greatly outperforms the baselines in all metrics, of course, in all datasets. So then we evaluate the efficiency of LTP trace. Since our method only need to add noise to key features, it is much more efficient than previous methods. And we also find that our synthesized trajectories are robust to various attacks. For example, more than 88% of trajectories can be successfully protected in re-identification attack, and almost all trajectories can be hidden from outliers. So here is the conclusion. We propose the first LDP trajectory synthesis algorithms, which can strictly satisfy the local differential privacy without relying on any external knowledge. And we propose a neat and effective framework to extract key patterns for generation with very few computational overhead. We also provide the theoretical guarantee to the algorithm capacity, and extensive experiments show that LDP trees outperform previous methods by a large margin. So thanks for your listening. Our code and database are all available on GitHub. If you have any questions about our work, feel free to contact me. Thank you.